with I had an unstable internet this morning. So if there is any problem, please tell me immediately and I will try to fix it, okay? Okay, so, and I don't see myself, but I hope you can see me. Is that true? Can you see me somehow?
Yeah, we see you another of you.
Okay. Okay. So whatever. So let's. Oops. So let's start. So the plan. Let me begin by, as always, tell you what the plan is for today. We ended last or yesterday with the start, and now what happened? Now I don't know how the pen works. Just 1 second. Okay, this is very good. I have a proposal. Can you stop the recording and we start over again? I think I have to switch again. It somehow doesn't work and I don't understand why. I don't understand what's going on here.
Okay, it's okay. What's the problem?
The problem is that I don't know how to use the, you know, I wrote today and then suddenly now I cannot use the pen anymore. And I don't know what's going on. I don't know how to make it work. And nothing reacts.
Did you focus down at the Windows or something?
I have no idea. Okay, listen. Let me switch. Let me switch if that's possible. Okay, now everything is frozen. Yeah, I told you I had some problems this morning. Okay, let me. Okay, I will be right back. No matter what happens in the next minutes, I will be right back, okay?
Okay.
Sorry
take time.
Okay. And this. Okay.
Okay.
Sorry about that. Yeah. No. This. Okay. And I hope now everything should be fine. Is it okay? Can you hear me?
We can hear you. And can you try to write something?
Yes.
Okay.
Hi.
Okay, great.
Okay, great. Okay, so let's start. Sorry for this. Okay, so let's start over again. So the plan for today. Oops. Is the following. Yesterday we started the proof that Martin's maximum implies that 2 to the LF1 is LF2, so it gives a bound on the size of the continuum, and actually, because we already know that Martin's axiom sub omega 1 implies that 2 to the LF0 is equal to 2 to the LF1, Sutherland's hypothesis, so that means that the continuum also has size LF2. That's kind of peculiar. And I actually want to, before we continue with the proof, we just started out and then we stopped. Before we start with the proof, I want to go back to a brief discussion of stationary sets and of the very first, or I guess the second theorem which we proved, namely splitting stationary sets in many stationary sets. We have to take another look at this argument. And actually, I think it's worth it to go through this argument carefully, because this is we will make use of a non-trivial forcing which preserves stationary sets. And, you know, we didn't see that many examples yet, so it's always worth it to go through these examples carefully. I assume that many of you didn't yet, or some of you didn't yet see these kinds of arguments. So I think it's interesting. Okay, so before we start out, we want to discuss some aspects of stationary sets. Okay, and then after we are done with the proof that Martin's maximum implies that 2 to the LF1 is equal to LF2, we want to move on to what one could call effective counterexamples to the continuum hypothesis. Just at this point, in order to get motivated, what does effective mean? So we will then have proven that Martin's maximum implies that there are LF2 many reals, so the continuum hypothesis is false. This is the continuum hypothesis. Okay, so in other words, if the continuum hypothesis is false, there is a surjection of the reals onto omega 2. This statement is just the fact that CH is false, but there will, for such a witness to the fact that CH is false to be effective, it means that we can look at the following. If you have such a function, you can look at the binary relation on R given by, for instance, like this, right? You say that X is related to Y if and only if f of X is less than or equal to f of Y. So this is a relation on R, and now you may wonder what is the possible complexity, or what is the least complexity of this relation. And it turns out that that under under Martin's maximum, we may pick such an f such that, so let's write R sub f for this relation. so that this relation R sub f is actually projective. And I think it's delta 1, 3, if I'm not mistaken. Okay. So that's the meaning of there are effective counterexamples to the continuum hypothesis. So they are kind of very simple. So in particular, there is a counterexample to the continuum hypothesis which exists in L of R, which is the least inner model which contains all the reals and all the ordinals, the least inner model of ZF, which contains all the reals and all the ordinals. So under Martin's maximum, this kind of small model contains already a counterexample to the continuum hypothesis. And the proof of that is more delicate than the proof of the fact that MM implies that 2 to the aleph 1 is aleph 2. Okay, so this does not give effective counterexamples, the proof we are going to give. Yes, okay, so what is the meaning of projective? You know what? I would suggest that we enter this discussion when we come to this topic, right? Because I want to talk about, we can then talk about what does it mean for something to be projective. We will also be interested in other complexity classes. So I suggest that we defer the definition of that for later. And for now, we just focus on proving this theorem, and then we will move on, if that's okay. 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 Okay, so the first topic is this theorem, according to which Martin's maximum lies at 2 to the aleph 1 is equal to aleph 2. And well, now I said we have to step back and we have to think about one thing before we start out. And let us go back to the proof that we can split stationary sets into many stationary sets. Okay, so before we really start out the proof, I want to verify the following claim, and it's really just taking another look at an argument which we gave 2 days ago. Okay, so I want to say the following, that we can write omega 1 as the disjoint union, I apologize, of aleph 1 many stationary sets. So let me write it down a bit more careful. So there is a sequence Ti I less than omega 1 such that omega 1 is the disjoint. So the dot over this union symbol always means that the union is supposed to be disjoint. So any two different objects there are pairwise, are disjoint with each other. Each Ti is stationary. We already know that that is true. But what I want to add here is that for each S being a subset of omega 1, which is stationary, there is an I less than omega 1 such that S intersect Ti is still stationary. Okay. We did not yet talk really about the non-stationary ideal and anti-chains and so on. We will have to do that in the future. What that actually means is that the collection of the Ti's is a maximal anti-chain. So every stationary set which exists at all is compatible with one of the stationary sets from that list, in the sense that the intersection with one of them is stationary. Okay? Yeah? Was there a question? So how do you, in other words, we can simply in ZFC construct such an anti-chain. Okay, so how do we do this? We just go back to the proof we had on the splitting, right? So let me sketch what's going on, and that's a nice way of repeating stuff we did. So remember, so back then we were splitting a given stationary set in many stationary sets. Now basically the stationary set which we want to split is ℙ1 itself. Okay. So the proof started out by saying, okay, for every psi which is less than ℙ1, and let's say which is a limit ordinal, every limit ordinal below ℙ1 has cofinality omega, so we pick a witness to that fact. So you pick a sequence of A and xi's which converge to xi. So let me just write it like this, okay? So there is an omega sequence of A and xi's which converge to xi with supremum xi, and let's say they are strictly increasing if you want, it's not necessary, which witnesses that the cofinality is omega. And then we were verifying the claim. Now let me write subclaim because we are dealing with a claim. We verified the subclaim that there is a natural number n, so that for every alpha, the set of all xi, now before we had written which is in our given stationary set, now the stationary set is all of ℙ1. So that alpha sub n of xi is at least alpha, that this is always stationary. Okay. Okay, let me not repeat the proof of that. The proof of that was simply you assume that that's not the case. So for every n, there is an alpha, so the thing is no longer stationary. So you pick a club which is disjoint. But then the intersection of omega many clubs is club again, and you're given omega many alphas, and which are all less than ℙ1, and you take the supremum of them, and then you get a contradiction. So that's very easy to verify. Okay. So let's just fix such an n. And then we continue exactly as before. What we do is we define a strictly increasing. Now I'm organizing it slightly differently to how we organized it before, but essentially it's exactly the same argument. So you define a strictly increasing sequence of, let's say, alphas. Alpha, maybe beta is better because there are too many alphas around here. Beta I discontinuous. So discontinuous means that beta I is always strictly bigger than the supremum of the beta j's, j less than I. Okay, such that the following holds true. The xi is less than ℙ1, so that alpha and xi is in the interval, the sup j less than I of the beta j's, comma, beta I. Okay. Maybe I should add a +1 here. Okay. Okay, so this is a non-empty interval, what I'm writing here. I look at the supremum of the beta j's, j less than I. So I look at all the ordinals, in the half-open interval between the supremum of the beta j's, j less than I, and beta I. And I just take the xi's so that alpha and psi is in that interval, and I call that set T sub I. Okay, so what I can do is I define a strictly increasing sequence which is discontinuous and has the property that all of these Ti's are stationary. Right, why can I do that? I can do that exactly because of that subclaim. If you already chose a strictly increasing discontinuous such sequence of betas up to some I, and now you're supposed to pick beta I, just look at the supremum of the beta j's for j less than I, right? And add 1 or something, and then just go to the subclaim and apply it to alpha being the supremum plus 1 of these things, and you will see that, you know, the set of psi, so that alpha and psi bigger than that supremum is actually stationary. And then by Fodor, you can actually press down, so above this bound, you have a stationary subset where the alpha and psi's have one common value above the supremum. Okay, and then you just take the dex beta I bigger than that thing. So maybe it would be good to write it down. So this is a simple recursion. What's going on? Now today everything goes wrong. Let's see. Okay, suppose the beta j's, j less than I, are already chosen with the property so far, okay, by the claim. The set of all psi, so that alpha n psi is bigger than the supremum of the beta j's, j less than I. This is stationary. And then by Fodor, there is some beta bigger than that supremum, so that the psi is less than omega 1. You know, this is a regressive function. If you map psi to alpha n psi, right? If you have a psi here, the alpha n psi's are all smaller than psi, and they soup up to psi. So there is a beta above that supremum, so that the psi is less than omega 1, so that alpha n psi is actually just equal to beta. This is also stationary. And then you just say you pick, let's say, beta I is, for instance, just beta plus 1 for such beta. And then if you step back and look at things, what you did, you verify that the Ti, which I wrote down on the previous page, is stationary, is stationary, right? So Ti is equal to all the psi's, so that alpha n psi is in the interval between the supremum of the beta j's and beta I. This is a set which is a superset, which is a bigger set than the set in this line here. Okay, so this is bigger, so it's also stationary. And of course, because the beta i's are strictly increasing, this is how we define the sequence, they are pairwise disjoint. But on the other hand, you know, that their union is all of omega 1 if you define T0 the right way, I guess. Okay. Okay, and now, so this is the construction. So this is how you split omega 1 into omega 1 many pairwise disjoint stationary sets. And it has the additional feature, it has this additional property which we want to verify. Namely, now let's look. So this defines this sequence. And now let S be your favorite stationary subset of omega 1. Okay. Then we kind of do the same thing, right? So we look at, for xi in map to alpha in xi, which is smaller than xi, so this is a regressive function. So there is by Fodor, there is a containing S, which is still stationary, and there is a alpha, so that the set of all xi in S bar, I should write it as follows. I can just say that S bar is equal to the set of xi's in S, so that alpha in xi is equal to alpha. Okay? But then this alpha has to be in one of these intervals, right? I mean, I said before, you have to define T0 in the right way. So T0 is just the set of all, there is no supremum. So I guess the supremum of the empty set, is it 0 or something? You have to say that the supremum of the empty set is 0 in order to get omega 1 actually being the union of all these things. Okay, anyway, this alpha has to be in one of these intervals. It's a partition of omega 1 into intervals, these things. So this here. The supremum. Right, so what I was talking about is that if I is 0, I want that the meaning of this supremum is just 0. So every ordinal is exactly in one of these intervals, so the alpha has to be somewhere. But then, right? But then if you look at S intersect Ti, right? This is a subset. This is a subset of S bar. And S, I'm sorry, S bar is a subset of that. Okay. And S bar is stationary, and therefore Ti intersect S is stationary. So we verified that the proof we gave actually gives us a splitting of omega 1 into omega 1 many stationary sets, so that whenever you give me another stationary set S, S has stationary intersection with one of these sets. Okay? Good. Okay, and this is something we have to keep in mind because this will become important in the proof which we are now going to start. So now we are going to start the proof that Martin's maximum implies that 2 to the Aleph 1 equals Aleph 2, and hence 2 to the Aleph 0 is equal to Aleph 2 also. Okay. So we fix. So we split omega 1 into omega 1 many stationary sets exactly as we did now. Okay, so you write omega 1 as the disjoint union of Ti's I less than omega 1. I don't know what happens here. each ti stationary, and for all, let me say t subset of omega 1 stationary, there is an I less than omega 1, so that t intersect ti is still stationary. Okay, so this is one thing we fix, and the other thing we fix is what we also discussed already yesterday, that you say I look at the points below omega 2 which have cofinality omega, and I want to split this set also into omega 1 many disjoint set, and that's possible exactly by the very same argument we went through just now. This is exactly the same argument. So for each point in S omega 2 omega, you can again pick a strictly increasing sequence of alpha and xi's which converge to xi, and then you repeat exactly the argument we just did, and this gives a splitting of this set into actually Aleph2 many stationary sets, but we don't need that. We only need a splitting into Aleph1 many stationary sets. Okay, so we split this thing into sets Si, I less than omega 1, such that each Si is a stationary subset of omega 2. So these sets live on different cardinals, right? The TIs, they are subsets of omega 1. The SIs, they are subsets of omega 2, right? So they live. Okay, and now what we want to do is, so this is fixed once and for all. And now for every capital X, we want to find the right reflection point. So we let X be a subset of omega 1, and we want to say that X is non-empty. Okay, so the goal is, and for this goal to be achieved, we need Martin's maximum. So what we want is that we aim to find an alpha which is also below omega 2, but it has cofinality omega 1. Such that the following holds true: Si intersect alpha is stationary in alpha if and only if I is an element of X. Okay. Okay, once we achieve that, I only need one line to write a bit more. Maybe I say it and then I write it down later. Look, so suppose you can do that for every capital X subset of omega 1, right? So you may associate to such an X the least alpha with this property. Okay. But now the last line, this is an if and only if. So in other words, if you have an X which is different from Y, then you cannot associate the same alpha to them, right? Because, well, that's trivial, right? I mean, you cannot have the same alpha, and then you have that, you know, there would be an I, let's say, which is in capital X, but not in capital Y, or the other way around, right? But from alpha, you can compute X completely, right? If you have alpha, then you just look at the question whether Si intersect alpha is stationary in alpha, and if so, you have to be in X, and if not, then you're not in X. So alpha kind of modulo the SIs compute X. So the function which sends X to the least alpha with this property, this is an injection. And therefore you have an injection from the power set of omega 1 minus the empty set into omega 2, and that gives that gives the bound on 2 to the Aleph1, namely that 2 to the Aleph1 is at most Aleph2, and therefore it's equal. Okay, so this gives, so the map which sends x to the least such alpha is injective, and therefore 2 to the Aleph1 is at most Aleph2. Okay? Okay, so this thing in the box is our goal, and now we have to design a forcing which does the job for us. Okay. And I already wrote down the forcing yesterday, but let me write it down again. So we will use Martin's maximum to prove this. To prove that for every such x we get an alpha. So maybe let me repeat what we are trying to show here. So the subclaim is, if x is a subset of omega-1, x non-empty, then there is an alpha below omega-2 of cofinality omega-1, so that what did I say? So that SI intersect alpha is stationary if and only if I is an X. This is what you want to verify. So the forcing which helps us here is the following. We say that P is in the forcing if and only if. So you want to do the following. If there is an alpha less than omega-1, so that P is a function from alpha plus 1 into S into the points of cofinality omega below omega-2, and it's normal. We already said what normal means yesterday. So normal means that for a limit ordinal lambda less than or equal to alpha, P of lambda is the supremum of the P of betas for beta less than lambda. For a limit lambda less than or equal to alpha. Okay. But also you want to have the property that for every eta less than or equal to alpha, and for every I, eta is in Ti. If and only, if eta is in Ti, then P of eta is in S f of I. So this is a function which I already wrote down yesterday. So f is supposed to be a function which goes from omega-1 into omega-1, so that the range of f is actually equal to x. Here you need, of course, that x is a non-empty set, and then you can do that kind of thing, right? Okay, so this is our forcing. So you say that P extends Q in that forcing if it's just an end extension. Okay, what does the forcing do for you? Okay, let's reflect a little bit what the forcing does. So suppose you force with this forcing over V. What does it do for you? It's fairly easy to see, and in fact we will verify something even stronger in a second. That the set of all alpha less than omega 1, so that the domain of P has alpha in it, that's a dense set. So in other words, if you pick a generic filter, then for every alpha less than omega 1, there will be something in the generic filter which has alpha in the domain. In other words, if you take the union of a generic, then this will give you, because things are pairwise compatible, the union of a generic will be a function from omega 1 into S omega 2. So if G is V generic for P, then the union of G will be a function from omega 1 into S omega 2, but you will keep the additional properties, right? So you will have the following. You will have that, right? And now you have that for all etas whatsoever less than omega 1, and for all I, if eta is in Ti, then now I may write the union of G. So this is this function here. At eta is in S f of I. Okay, let's reflect on what that actually means, right? So let's take a point J which is outside of the range of f. Remember that the range of f is exactly x, capital X. If something is outside of x, let's call it J, right? I mean, the union of the Ti's is just all of omega 1, right? So if eta is in Ti, then the function at eta is in S sub f of I. So every value of that function is in one of the S sub f of i's. So you're always outside of S sub j if j is not in the range, right? So if j, I have a leg of space here. So this is an easy part. So let me erase that, and let me write. Okay, so this implies that if j is not in is not in X, which means that j is not in the range of X, then the range of this function intersect S sub j is empty, right? But the range of the union of G, remember that all the conditions in P are normal. So the function union G is also a normal function. So its range is a club. So here we have a club which is disjoint from Sj. So what you did is you shot a club through the complement of S of Sj. So Sj is no longer stationary. And when I say it's not stationary in the extension where we did the forcing, right? Okay, but on the other hand, if j is in X, so if j is in the range of X, let's say j is f of I, right? Then you have the bottom line. So if eta, so let's say j is equal to f of I. So whenever eta is in T sub I, then the union of G at eta is in S sub f of I. So that means that you kept S sub f of I as a stationary set. because kind of the stationary set downstairs, Ti, just gets shifted up into, you know, the pointwise image under the function union G of T of I is a stationary subset of S sub f of I, and therefore the pointwise image of this Ti is stationary, and therefore, because it's a subset, S sub f of I is still stationary. So what I have here is an if and only if. So on the other hand, if J is an X, then S sub J is still stationary. So we kind of have exactly what we want. Okay, now we've forced over G, but in the application of Martin's maximum, this is not what you're doing. Okay, but we will come back to that point. Let's first verify if you want to apply Martin's maximum, you can only apply it to forcings which preserve stationary subsets of omega 1. So this is something important which we now want to verify. So how is the rest of the argument organized? We defined this forcing. We already argued a little bit what happens if you actually force over V with the forcing. But this is not what's gonna take place when you apply Martin's maximum. What you want to do is you first show that the forcing preserves stationary sets, and then then we have Martin's maximum, and it says if whenever you have a forcing which preserves stationary sets, and whenever you have a collection of LF1 many dense sets, then there is a filter in V which meets them all, and this is what we are gonna do. So the first task is that we verify that the forcing preserves stationary sets. So there is a subclaim, or is it a claim now? I forgot. I think I can write claim. P preserves stationary sets. Okay, and this is where it becomes important how we chose the collection of the T sub I as being a maximal anti-chain, so that we chose them in a way that for every stationary set there is one of them, so that the intersection is still stationary. Okay. And this is a typical proof of the verification that a given forcing preserves stationary sets. These arguments can become very complicated, and for instance, in the proof of David Asbro and myself that Martin's maximum double plus implies Woodin's axiom star, this was the key thing, to cook up a forcing which does what you want, and you can prove that it preserves stationary sets. So the proof that a forcing preserves stationary sets can be the hard part of the whole story. And it's sometimes highly non-trivial. Here it's kind of not that hard, but it's not trivial, really. Okay, so what do you want to do? Right, so we are fix your favorite stationary subset of omega 1. Okay, and also we want to show that it's still stationary if we force that it's still stationary in the extension. So what we do is we pick a name for a club and let's say P forces in the forcing P that C dot is a club. Okay, so what we do is the following. T is a stationary set. So there is this I less than omega 1 such that T intersect Ti is still stationary. Okay, now we use this additional property of the sequence of the Ti's. Okay, and now what we do is, okay, now we look at S f of I, right? Remember, f is this function which goes from omega 1 to omega 1, whose range is exactly capital X. Okay, so this is a stationary set. So it's a stationary subset of omega 2, or in fact of the points less than omega 2 which have cofinality omega. Okay. So what we can do if you have such a stationary subset of omega 2 we can pick a substructure of V or of some large H theta. So theta is just some big regular cardinal, let's say. I want to have a substructure which has size LF1 and such that X intersect omega 2 is an element of S sub F of I. Why is that possible? Well, just look at the chain of such substructures where you make the X intersect omega 2 strictly increasing. You already used X. That's true. Thank you very much. Okay, I should, so let me write a small x here. So that is a small x. The capital X was the given subset of omega 1, which we want to kind of code by alpha. Thank you. So okay. Okay, so how do you get such a thing? Well, you look at a chain of a continuous tower of such substructures, which are substructures of H theta, and all of them have size LF1, and you make the X intersect omega 2 strictly increasing. And then if you look at the X intersect omega 2 for X's from the tower, that's a club. And then one of the X's has to have the property that X intersect omega 2 is an actual element of S sub F of I, because that's a stationary set. Okay, so there is no problem with that construction. But now, once we have that, we may pick another substructure. I guess now I can write a capital Y, it doesn't matter. Okay, now I want to pick a countable substructure such that two things hold. I want to keep the supremum with the intersection with omega 2. So I want to have that the supremum of Y intersect omega 2 is the same as X intersect omega 2, and this was an element of S sub F of I, right? That's no problem, because I can pick a witness to the fact that X intersect omega 2 has cofinality omega. Remember that X intersect omega 2 is an element of S sub F I, so it has cof omega because S sub F I is contained in all the points of cofinality omega. So I just pick a witness to that fact, and the points from that witness, they are all in small x. Okay, so I put them all into my substructure, and then I form another tower which has these countably many points. I form another tower of substructures of length omega 1. I look at which are all countable, and I look at their intersection with omega 1. So that's again a club. And then the points from that one of them has to be in T intersect T sub I, right? So what I want is that Y intersect omega 1 is in T intersect Ti. This is a stationary set, so I can do that. Okay. Okay, so here now I have a countable substructure Y of H theta, so that the supremum of Y intersect omega 2 is in S sub Fy, F of I. So I have this property. And I have this property that Y intersect omega 1 is in T. Okay, or in both T and Ti. Okay, so now we continue with a construction which is very familiar for people working in this area. So now you construct a sequence. Okay, you start out with this P. This is the condition which forces that C dot is a club. So you call it P0. and you form a increasing a sequence of things getting stronger and stronger, so that individually all the PNs are supposed to be in the substructure. Why? Okay, I didn't write it down. We could have said that little p and all the other points of current interest, they are in small x, and they also end up in capital Y. These are only finitely many things which you always can throw in, right? So with our loss of generality, little p and the forcing and the name for the club and so on, they are all supposed to be in capital Y. Okay, so you may construct a sequence of PNs so that individually the PNs are all in Y, but you need one dense set of Y after the other, right? So that for all D, a subset of P, D in capital Y and D dense, there is an N so that Pn intersect D is non-empty. Okay. So that's no problem, because capital Y is a countable set. So you can just construct a sequence of stronger and stronger conditions which meets one of these dense sets after the other. And the effect of that is that if you look at the domain of the PNs, or let's look at the soup of the domains of the PNs, this will be exactly Y intersect omega 1. So one consequence of that is that the soup of the domains of the PNs is equal to Y intersect omega 1. And also the soup of the ranges of the PNs is equal to the soup Y intersect omega 2. So this thing is in T intersect Ti, and this thing is in S sub Fi. So I want to look at the union of the PNs. So that is almost a condition. The problem is that the domain of a condition has to have is to be a successor ordinal. There has to be a last point, if you remember the definition. And this thing, the domain of that thing, of the union of the PNs, this is a limit point. This is exactly equal . Okay, and here the N is in the wrong spot. Okay. So the union of the PNs is not a condition, but for instance, another effect of meeting one of the dense sets after the other is that whenever you give me a point, an ordinal below Y intersect omega 1, then there will be an N, so that Pn forces that there is something about this point which is in the club, and this something which is in the club is again in the substructure, so it's smaller than Y intersect omega 1. In other words, Y intersect omega 1 is kind of forced to be a limit point of the club. So if I can extend the union of the PNs to a condition, then that condition will automatically force that Y intersect omega 1 is in the club. But Y intersect omega 1 is also in T. So we will have forced that the intersection of T with C dot is non-empty. Okay, but what is the condition which extends the union of the PNs? You simply say that at Y intersect omega 1, I take the value soup y intersect omega 2. So this is a condition. Right. This is possible. This makes it a if you look at the definition of P, you have exactly all the properties. So you have the property in the last coordinate because y intersect omega 1 is an element of Ti, and the supremum of y intersect omega 2 is an element of S sub f of I, and that's exactly what you want for a condition. Okay, and also the function was extended to a normal function. So this is a condition, and as we just discussed, this condition now forces that y intersect omega 1 is a limit point of C dot, so it's an element of C dot because it's already forced by P that it's a club. But y intersect omega 1 is also in T, so this condition, it forces that T intersect C dot is non-empty. Okay. Okay, so this was a verification that the forcing preserves stationary subsets of omega 1. Okay. And now you just write down the collection. Now let's apply, oops. So in the application of MM, now we have to write down the right Aleph 1 many dense sets in order to get something useful, right? So we have this forcing, right? We have this forcing. So a typical forcing condition is a function from alpha plus 1 into S omega 2 omega. And we said that we want that if now let me write it. So this is a normal function. Oops. So that if xi is in Ti, then P of xi is in S sub f of I. For all xi less than or equal to alpha. Okay. So for instance, if you put down the dense sets, you know, for every alpha, the set of all P, so that alpha is in the domain of P, this is always dense for all alpha less than omega 1. Okay, so if you meet all of them, right, we want to write down Aleph 1 many dense sets, so if the filter meets all of them, we get something useful. So if you meet all of these sets, then the union of G will be a normal function from omega 1 to S omega 2 omega. So if you look at the range and call it C, this is a club. Of course, if you pick the G, if you meet all of those by a filter G, I should say, right? Of course, if you meet, if G is in the ground model V, then this function union G, it cannot be cofinal in omega 2, right? Because you cannot have a normal function from omega 1 into omega 2, which is cofinal. So there will be a bound, but then the bound, because the function is normal, will be a point strictly below omega 2, which is cofinality omega 1. And this is our alpha, which we want to get, okay? Is a club. So set if G is in V, then the range, or then the sup of C is strictly below omega 2, in fact, let's call it alpha. This is an element of S omega 2 omega, omega 1, I should say, right? Okay, and then we have all these properties, right? Because we have that, there was an I missing here for all I less than omega 1. So we will have that for all psi less than omega 1 and for all I less than omega 1, psi is in Ti implies that this function at psi is in S of Fi. And as we discussed before, the same thing now yields the following. If let's say J is not in X, so J is not in the range, then C intersect S sub J will be empty because of the line above. But if J is in X, then, you know, T sub, okay, say J is equal to F of I, okay, then the pointwise image of Ti is stationary. Ti is stationary. So this is a subset of S sub Fi, and this is then also stationary. Okay. I'm getting a notification that my internet connection is unstable. So if anything pops up, please let me know if there is a problem. Okay, so we have exactly what we wanted. We have that J is an X if and only if S sub J is stationary. And this verifies the claim, and therefore 2 to the aleph 1 is aleph 2. Okay, as we discussed. So the only right, so there is this, we have this, so the way it works is the following. We cook up a forcing, or we have a natural forcing, which we call P, which kind of does the job we want. So we verify that the forcing preserves stationary sets. Then we write on the right aleph 1 many dense sets. In this case, it was just these sets up here. And then we show that if we meet all of them by a filter, this filter gives rise to an object like we want to have it. So in this case, the filter gives rise to the union of G, the filter G gives rise to the union of G, and this will be a function which actually witnesses the statement we want to have, namely that I is an X if and only if S sub I intersect alpha is stationary. Okay. Okay. So this ends the proof. And maybe I should summarize what's going on here. 2 to the aleph 0 is equal to 2 to the aleph 1, and this is equal to aleph 2. Okay. Is there any question on this proof or anything we did up to this point? except for the question which was asked, what does projective mean? But we will come to that, I promise that. So we have a little bit of time until the break. I said that now we want to move on to showing that MM implies that there are effective counterexamples to the continuum hypothesis. And in fact, the first person, as far as I'm aware of, who verified this is Fudan. So this was first verified so the result that under Martin's maximum 2 to the aleph 0 is equal to 2 to the aleph 1, and this is equal to aleph 2. This is in the original paper by Foreman, Magidor, and Schindler on where they introduced Martin's maximum. And then there was the open question whether you would or could have an effective counterexample to the continuum hypothesis under Martin's maximum. And then later Fudan came and said, yes, that's the case. One can actually prove it. In fact, he proved the result that if the non-stationary ideal on omega 1 is saturated, plus you have a measurable cardinal, then delta 1, 2 is aleph 2. Whatever the ingredients of this statement mean, but this shows that under MM there is an effective counterexample to the continuum hypothesis. And I now want to go ahead and explain the concepts which are involved in order to verify this kind of thing. Okay, so I would like to do it slowly, and I hope that it's okay with you. So what the plan is now, I first want to introduce the relevant concepts in order to be able to formulate and show that there is an effective counterexample to the continuum hypothesis. So we will have to talk about iterations of V or inner models by total or partial measures, and then we will have to talk about iterations of V or smaller models via precipitous ideals on the omega 1 of the respective model. So this is all background material I want to make part of this series of talks. Okay, so we will have to start a new topic now, which is kind of independent of what we did so far, but then after we did that, we will come back to discussing these consequences of MM. Okay, so we will need some background. On iterating V or smaller inner models by total or partial measures. And you can also iterate V or smaller inner models not only by partial measures, but by ideals. And if you iterate via ideals, it's called a generic iteration. So sorry for my handwriting. So this says we will need some background on generically iterating V or smaller inner models by total or partial measures or ideals. And we have to talk about that for a little while. Okay. Okay, so before the break, maybe we should simply, I wanted to tell you, yeah, I mentioned it. So the result, before we continue, I want to say that the result which we proved at that point, so MM implies, I promise you to always give references. So MM implies 2 to the LF1 is equal to LF2 is in the original paper by Foreman, Magidor, Schindler. Yeah, I have a problem with my tablet, Schindler, on Martin's maximum. Okay, you will have no problem finding that paper. Okay, so let's start by in the remaining few minutes until the break. Let's discuss iterations, and I also want to say a few words on sharp for reals. Okay. Okay. So iterations of V. So when we iterate V, we need a measurable cardinal. So the starting point is U a measure on some kappa bigger than omega. So in this context, what do I mean by a measure? A measure meaning a non-principal less than kappa complete. Sometimes you add normal, but we don't need that. Ultrafilter on kappa. So a filter on kappa is a collection of subsets of kappa so that the intersection of any two of them is also in, and supersets of things in the filter are also in the filter. But let's say the empty set is not in the filter, but it's a non-empty thing. Less than kappa complete means more than that the intersection of any two of them is in the filter. You take any, if you have less than kappa many in the filter, then the intersection is also in the filter. Normal would mean that it's closed under diagonal intersections. Ultrafilter means that every subset of kappa is measured in the sense that either, if you take your favorite subset of kappa, then either that thing is in the filter or the complement is in the filter. And finally, non-principal means that, well, the filter is kind of non-trivial in the sense that singletons are not in the filter. You can always define everything up to that point, what I said, by saying I pick an ordinal psi less than kappa, and then my filter is given by anything is in the filter, something is in the filter if and only if psi is in it. That gives a less than kappa complete ultrafilter on kappa, but it's not very interesting. So non-principal means that singletons are out, which is equivalent modulo the rest, that every element of that filter is, the filter is uniform in the sense that every element of the filter has size kappa. Okay, so once you have that thing, there is an alter power construction. So you start out with V, and you may make sense of the alter power of V by U, and you get an embedding J. Okay, so I don't want to go into that because we don't really need it, and I would like to presuppose this. So what's going on here? You have this ultrafilter, so there is a general model theoretic construction if you have an ultrafilter to get such an alter power. So what you do is you look at the collection of all functions f from kappa to the universe V, and you factor, you say that two functions are equivalent if and only if they have the same value on a measure one set, on a set in the ultrafilter. And you say that and then you build equivalence classes, and then you say that one equivalence class is a pseudo element of another equivalence class if the points where the first function is an element of the second function is of measure one is in the filter. And then you show by completeness that this is actually a well-founded relation. So you may look at the transitive collapse of the collection of all the equivalence classes of these functions and equipped with a pseudo epsilon relation. So this will give you a transitive structure. And then you may define an actual elementary embedding from V into that, what you now call the alter power. So X is mapped to the image under the collapse of the equivalence class of the function which constantly has value X. And there is Wasch's theorem, and you can verify everything. So this is a construction which, for instance, you can very nicely read in Tom Yak's book, or if you want in my book, this alter power construction. So I don't want to say much more on that. What is important to us is something that we can iterate this process. So what does that mean? So we start out with V, which then we call M0, and V has a U, a measure on kappa, in the sense as we defined it on the previous slide. So we can define the alter power of V by U, okay? And we transitivize it, it's always well-founded, so we take the transitive collapse and we call it M1. Okay, and because the embedding J from here to here, which we now call J01, this is an elementary embedding, so just by elementarity, M1 will have J of U as a new measure, and because we will continue, we now also call U0. So this model U1 will have as an element U1, which is just J01 of U0. And then we may repeat the same process. Okay, but this is always internal. So M1 thinks that U1 is a measure on J01 of kappa. So we may simply consider the alter power of M1 by U1 and call it M2. And again, it's well-founded because by the same argument, by the result that if you have a filter which is complete, then the alter power is well-founded. Okay, and then that way you may continue. So you have Mn, which is always the alter power of Mn minus 1 by Un minus 1. Everything's defined in a straightforward way. And you can actually also continue to the limit step because this is a direct limit system, right? So you can make sense of a direct limit, right? So there is a least inner model, or there is a least model M lambda, so that every point in M, not lambda, I'm sorry, in omega for now. So there is a least model M omega, so that every point in M omega is the image of something coming from an earlier model, and so that the whole diagram commutes. Okay, so now you can actually prove that M omega is transitive, and this is something I want to prove, but maybe we can do that after the break. And once you show that M omega is transitive, you're back to the same situation. Then you have the image of the original U in M omega, and it is again a measure from the point of M omega. So you may take the alter power of M omega by that image, which we call U omega, and you call it M omega plus 1, and so on and so on, and you go throughout the ordinals, and this is and you show that, well, at successor stages, you never run into an ill-founded model because it's internal. So it's the same argument as in the very first step. The alter power is well-founded. And at limit stages, you need a new argument to show that the limit model is also well-founded. And this is something I want to not start now, but do after the break. So once we showed that, we showed that V is iterable by a given measure and its images. And this will be important, and we will actually need a generalization of this to measures which are not even elements of V. And also to ideals in the sense that the measure, so a specific case of when the measure is not an element of V is when it's obtained by forcing using an ideal, and in our case it will always be an ideal on omega-1, and I will say how that works. So it's a little bit early, but I suggest that we make a break at this point.
Okay. Let's start 15 minutes break.
Sure. Great. So remember that the next goal is that we want to verify not only that Martin's maximum implies that the continuum is exactly LF2, but it also verifies that there are effective counterexamples to the continuum hypothesis in the sense as we indicated, I will make it more precise when we get there. There was also the question, what does projective mean? So I will make all that precise when we get there. But as a background, I wanted to talk a little bit about iterability because this is a very important concept. And when we said, and on the first day, I said that Fudan's work is everywhere in set theory. So this is, for instance, one spot where Fudan made very important contributions. Okay, so where are we at this point? So we started discussing a situation where V has an element U, which is a measure on some cardinal kappa. It's kind of nicer to write on the blackboards, but anyway. Okay, so we have a measure on some cardinal kappa, and by the way, if you have such a measure on the cardinal kappa, I think I didn't mention it, then the cardinal kappa is called measurable. Okay, and then we said that we may start out this process. So you have V, which then you call M0, you take the alter power of V. By that measure U, you call it M1, and then you just repeat the process. You take the alter power of M1 by J0, 1 of U, which then you call U1, and so on and so on. So in general, you have this commuting diagram, everything commutes. So you have elementary embeddings J and M between the various MNs. And at limit stages, you want to say that I take the direct limit M omega, so that's the least model, so that everything in it is an image of something from before, and that the diagram still commutes. So there is a unique object of that form that's called the direct limit. And if that thing is well founded, you again identify it with the transitive collapse, and then you just continue to M omega plus 1 as being the alter power of M omega by U omega, which is the image of the original measure, and so on and so on. So at limit stages, you always take the direct limit, and at successor stages, you always take the internal alter power by the current image of the measure. Okay, and we want to verify that this process never leads to an ill-founded structure. That's an actual theorem. So the linear iterability of V by a measure That's a theory. And let me prove this, because we will need that argument later, and it's maybe not that commonly known for the later application that I should give it. Okay. There is more than one type of argument showing that this iteration never leads to an ill-founded structure. There is a more modern one, which is a bit more model theoretically, taking just a countable substructure of the whole situation. It's a little bit more elegant, but unfortunately, when we want to apply this whole thing, the argument to generic iterations, we have to use a more old-fashioned argument, which, by the way, the old-fashioned argument can also be found in Tom Yeck's book on set theory. Okay, so let's assume, so we made sense of this iteration, right? So we said that at successor stages, we never run into an ill-founded model, so we may assume that all the successor models are actually transitive. And now we want to show that at limit stages, we don't run into an ill-founded structure. So let's take the least ordinal lambda so that we run into a problem, supposing that there is such an ordinal. Okay, so let me go to the next page. So keep this picture in mind. I want to have a little bit of space. Okay, so we consider exactly this situation. So we say that, say lambda is least such that m lambda is not well founded. As we said, the successful cases are internal, and you may just apply the result that the alpha power of v by a normal measure is always well founded by the completeness of the measure. So that's true in any model mi, if mi is well founded, and therefore mi plus 1, the alpha power of mi by this internal measure, is also well founded. So if if there is such a lambda, then the lambda has to be a limit ordinal. So what does that mean for a model of set theory to be ill-founded? You know, we have the following situation. If you draw a picture, so we have V, which is M0. We have all these intermediate models M gamma, and we have this final model M lambda, which is the first one, which is actually ill-founded. So a model is ill-founded means that its pseudo epsilon relation is ill-founded. So there is an infinite descending epsilon chain in the model. Of course, the model itself does not see this epsilon chain, but it's there. But the model M lambda is a model of CFZ because there is an elementary embedding from M0 into M lambda. So it's a model of CFZ. So if there is a strictly descending epsilon chain in the model, you may look at the ranks of the members of this epsilon chain, and this will give a strictly descending chain of ordinals of M lambda. So externally we would see a sequence of length omega of what M lambda thinks are ordinals, and it is strictly decreasing, right? So in other words, what is this? In other words, M lambda has a sequence of, well, non-standard ordinals, let's say alpha. So there is an alpha 1, alpha 2, alpha 3, and it goes down, right? These are not real ordinals, these are things which M lambda thinks are ordinals. And the model we assume is ill-founded, so it's a non-standard model. Okay, so you have this situation. So we have that from the point of view of M lambda, alpha 2 is less than alpha 1. From the point of view of M lambda, alpha 3 is less than alpha 2, and so on and so on. But the sequence we only see externally. The sequence we only see in V. Okay, now it's very easy to argue that there must be an alpha. You know, this alpha 1 comes from somewhere. It's a direct limit. So it has an image under something. Okay, so let's say alpha 1 comes from m gamma. Okay. So there is a pre-image in the gamma. The gamma model is well founded. So the pre-image of an ordinal is an ordinal by elementarity. So m gamma thinks that the pre-image is an ordinal, and because m gamma is transitive, as we assume, it is an actual ordinal by absoluteness. So there is this ordinal in m gamma, which kind of, whose image starts an epsilon descending chain of ordinals, but then there is an actual alpha in the original model V, so that the image of alpha under the map from here to the gamma model is bigger. Okay, that's kind of trivial. You could just take the ordinal in m gamma, add +1, and look at the image of that ordinal +1 and map it to m gamma, and you have this picture. So in other words, why can I not draw a straight line here? Okay. I don't know, somehow I cannot draw properly today on my tablet, but never mind. I hope you can see what I'm doing here. There is an I have to move this whole picture a little bit to the left. I don't know. Okay, alpha 0, alpha 1, alpha 2, and so on descending. This is an m lambda. Okay. So in other words, we argued that there is a pair. You know, we have lambda and we have alpha, and we may assume that this is the least, the lexicographically, such that, you know, if you look at pi 0 lambda of alpha, it starts, it's the top point of a strictly descending sequence of ordinals in m lambda. Starts a strictly descending sequence of ordinals in m lambda. Okay, there is such a pair, so that we may also minimize. We first minimized the lambda, we did that anyway, and now we minimize the alpha, so that if you look at pi 0 lambda of alpha, then there is this strictly descending sequence below it. Alpha 0 is bigger than alpha 1 from the point of m lambda, alpha 1 is bigger than alpha 2 from the point of view of m lambda, and so on. This is for what it means that this point starts a strictly descending sequence. Yes, can you hear me again?
Yes, I
Yeah, I was gone for a second. There's some internet problem today. Okay. Let's see, what did I want to write down? I wanted to say that, let's say alpha 0, what is pi? Where is the pi here? Let's see. I'm sorry. Yeah, I'm using pi for what I wrote, for what I call J. So the J's, sometimes I write pi, sometimes J, I apologize. So the J's are the map between the individual models. So there is always a canonical embedding from, let's say, the beta's model to the gamma's model, and this map I call J sub beta gamma. So there is a map J sub 0 lambda from V, which is M0, into M lambda. Okay, so we minimize first the lambda and then we minimize the alpha, so that J0 lambda of alpha stars a strictly descending sequence of ordinals. And then we said that everything comes from somewhere because this is a direct limit. So alpha 1 has a pre-image in one of the models. And let's say we take M gamma so that alpha 1 has a pre-image, and we call the pre-image alpha 1 bar. So alpha 1 bar is J of gamma lambda to the -1 of alpha 1. And we also move up alpha, so alpha 0 bar is the image of alpha shifted up to lambda, to gamma. But this is just the same as J gamma lambda to the -1 because everything commutes of alpha 0. Okay. Okay, what do we have? If we look at things, a key point is that the iteration is always internal, right? So V can see the whole iteration. But for instance, M gamma can see the whole tail end of the iteration. M gamma does not see the models which lead up to itself, but what it can see is it can see the alpha power of M gamma by the current measure. So it can see M gamma +1 in the map, but it can also continue, right? It can see the whole iteration which starts with M gamma. So it can see the rest. So what does that mean? So that means that M gamma thinks that there is this ordinal alpha bar less than the current image of alpha, which is alpha bar 0. But let me write J0 gamma of alpha, so that pi 0, not 0, pi, what do I have to write now? Yeah, I mean, I have maybe it's getting a little bit confusing if I write it down exactly. So what I want to say is that M gamma thinks that there is an alpha bar less than J0 gamma of alpha, so that if you move up alpha bar to the lambdath model, which is something which M gamma can see, then this starts a strictly descending sequence in M lambda. Okay, so this is something, let me not write it down because it will get a little bit confusing. Okay, so M gamma can see that there is an actual point less than alpha 0 bar, so that if you move it up to the lambdath model, then it starts a descending sequence. Okay, this is an internal statement about M gamma, and it can be, by elementarity, it can be mapped back to M0 to V. So by elementarity, there will be something which is less than alpha, so that if you move that thing up to M lambda, it will start a descending sequence, a strictly descending sequence in M lambda, but that then contradicts the minimality of alpha. Okay, so the argument is simply we minimize the pair lambda comma alpha lexicographically, so that J sub 0 lambda of alpha starts a strictly descending sequence of ordinals in M lambda. Then we go to the next point of this descending sequence in M lambda. It has a pre-image somewhere, but then that pre-image, which in the picture is called alpha bar 1, it's this point here, right? This point, if you map it up to M lambda, starts a descending sequence. okay, namely alpha 1, alpha 2, and so on. But it's smaller than alpha bar 0. So M gamma thinks there is something below alpha bar 0, which starts a strictly descending sequence when you move things up to M lambda. And then you pull this statement back to M0. So by elementarity, there is something below alpha, so that if you move it up to M lambda, it starts a strictly descending sequence. And that's a contradiction to the minimality of alpha. Okay, so this gives a contradiction. Okay, there are a little bit too many indices when you write it down formally. I think it's better to, in this context, to just talk about it. Okay, so now we need to, in order to proceed with the whole lecture series, we are kind of halfway, and we want to discuss effective versions of the failure of CH, but we also want to move on to Woodin's axiom star, and to even formulate Woodin's axiom star, we need the ℙmax forcing. And in order to do that, we need to generically iterate. So we have to discuss that, and that's something I want to do now. Okay. So we now want to take not internal alter powers by a measure on V, we want to take external alter powers. So there are two ways of external alter powers. The first one is when the alter power is external to the current universe, just because, well, it's not there because the universe is kind of slimmer than V and it doesn't have the alter filter. So let me do a very brief discussion of sharps. And I think we only need sharps for reals. So let X be a real. If you want, you can think of X as a subset of omega. So it could be, so for instance, if you have a measurable cardinal, you take the alter power of V and you restrict to L of X. L of X is the least inner model which contains X as a point and is a model of CFZ. You can also define it more carefully by, or more slowly by saying, well, I do the same construction as the constructible hierarchy, but I throw in X at the bottom. So I get a model which is constructible, but not just constructible from X. So if you restrict the alter power embedding from V into the alter power of V by a measure on kappa to L of X, you will get an elementary embedding from L of X into the image of L of X. What's the image of L of X? X is not moved because it's a real. So L of X will be made to L of the image of X, which is again L of X. So you get a non-trivial elementary embedding from L of X into L of X. Okay, J non-trivial. So what I just said is that in the presence of a measurable cardinal, you get a non-trivial elementary embedding from X into X. And if that's true, if there is a non-trivial elementary embedding from L of X into L of X, then you say that X sharp exists. So by way of definition, X sharp exists if and only if there is a non-trivial elementary embedding J from L of X into L of X. Okay, in order to work with things, it's actually nicer to rephrase the existence of X sharp in different ways. So it turned out kind of in history that the best way to rephrase it is in terms of mice, and I want to very briefly try to explain what that means. So in the case you have this kind of non-trivial elementary embedding from L of X to L of X, what you can do is you derive an alter filter on the critical point of that embedding. So let's say kappa is the critical point of such a j. So that's the least ordinal which gets moved to something bigger. Such an ordinal always have to exist if the embedding is non-trivial. Non-trivial meaning that it's not the identity. Okay, so then you can say I define U as the set of all subsets of kappa which happen to exist in L of x, so that kappa is in J of x. And you can prove that this U is not an element of L of x, but it behaves like a measure on kappa. You know, you can verify that it's an ultrafilter, so everything in the power set of kappa in L of x is either in or out. And it, you know, if you take less than kappa many, a sequence of less than kappa many elements of U, which is actually in the model L of x, then the intersection is also in that ultrafilter. It's non-trivial, it's non-principal. So it has all these properties. It has all the properties of being a measure on kappa, except for that the model L of x cannot see it. Okay, but we can make sense of the structure L of x together with this internal ultrafilter. So you may look at L of x together with U. U is now external to L of x, but it exists in V. And now we may do the very same construction as we did before when we iterated V. We may take the alter power of L of x by U. Because we derived U from the map from L of x into L of x, this actually factors. So the alter power of U by L of x can be re-embedded into L of x. And therefore the alter power of L of x by U is again well-founded. But what the key point is that you can also carry up U. You can do it pointwise. I'm sorry, you can kind of do it piecewise. So you can split up U into, you can write U as a union of things which are actual elements of L of x. You can prove that if you have any kappa-sized subset, if you have any set of size kappa which is in L of x, then that set intersect U is in L of x. And therefore you can split up U into pieces which individually are in L of x. You move up all the pieces and you put them back together, and then you can make sense of the alter power of U by the alter power map obtained by taking the alter power of L of x by U. Right? So in this situation, so if U is obtained that way, we can make sense of, you know, you have L of x, we have U, we take the alter power of L of x, this again gives L of x. So there is this map J, 0, 1 here, but there is a U1. We may just define it as J, 0, 1 of x intersect U1, and the union of that for x's which are in L of x, and x has cardinality less than or equal to kappa in L of x, for instance. So you split up. Wait a minute, there's a typo here.
You may want to use a different variable. You have 2x.
That's also true. I always use the same letters for everything. Thank you very much. So y is a good letter, no? Y in L of x, the cardinality of y being okay. Okay, so you break up. The detail is not important. The point is that you are able to break up U into pieces which individually are in L of x. So these pieces here, they are elements you can show of L of x. you move up the pieces and you just take the union of them upstairs and you verify that you're back to the same situation. That kind of, it's an external measure on L of x. And then you just repeat the process as we did before. So you get a J1, 2, again into the alter power. And there will be a U2. And now it's more difficult to prove that the alter power is actually well-founded. So this is a much more delicate argument. Before we said that successor stages are always okay because we're taking internal alter powers. And we have the fact that if you have a less than kappa complete measure, which we can actually see, then the alter power is always well-founded. This doesn't work here because L of x doesn't see the alter filter. And there are actually kind of fake alter filters. There are external alter filters external to L of x, so that if you take the alter powers, then you run into ill-founded structures. If you originally derived U from a full elementary embedding from L of x into L of x, then that's not going to happen. So there is a theorem which shows that this process, which I'm just about to describe, never runs into an ill-founded structure. So that's a theorem. Okay, and then you can continue. The feature here is that the underlying models, if you ignore the U, this is always L of x, as long as you're well-founded. And we said that if U is derived that way, it's always well-founded. It's never going to change. So every iterate has L of x as the underlying structure, but then the top measure will be kept moving up. Okay, so a typical ith iterate looks like L of x together with Ui. Okay, so these structures here, they might be called mice, and it turns out that it's not very helpful to carry all of x along. You may also carry a smaller initial segment of L of x along. So for instance, what you can do is you look at tau being the cardinal successor of kappa in the sense of L of x, and then you cut off L of x at tau, so you look at L tau of x together with U, and that is what we call a premouse. Such a structure, you derive U in the way we did it on the previous slide from a non-elementary embedding from L of x into L of x. You define tau that way. That structure is a premouse. It has the nice feature, because what I said above is that if you take an element of L tau of x and intersect it with U, that's in U. So that's what's called the amenability of U, or the amenability of that structure. And that structure is actually iterable in the sense as we just discussed it. So you can, for that structure, you can repeat the very same process which we did up there for L of x. You can do it for L sub tau of x, and you iterate. So you never run into an ill-founded structure. The only difference being that the underlying models of the iteration will now get longer and longer. So you will stretch out. So tau is the cardinal successor of kappa. So if you take the alter power, kappa is the critical point, so it's mapped up to something much higher. So the first alter power will be a model of the form L sub tau 1 of x, where tau 1 is bigger than the original tau, together with a new predicate, and so on. So that's an iteration, and it's highly non-trivial to show that if you start out with an elementary embedding from L of x into L of x, and you derive this object as I wrote it down here, that's iterable in that sense. If you want to see the argument, it's, for instance, in my book. Okay, but we don't want to go into that. We need to take these kinds of things as black boxes. So let me recap. So we said that by way of definition, the fact that x is a real. So by way of definition, we say that x sharp exists if and only if there is a non-trivial elementary embedding J from L of x into L of x. Okay, we said that we did not show it, but I said it, that this implies that there is a structure L tau of x u, which is iterable, right? So u in this situation, if we set up things as we did before, u will be an external measure on some kappa. Kappa will be the largest cardinal of L sub tau of x. Iterability means that I can take the alpha powers like we did before, and I carry along u because of this immutability fact that u intersect any element of L tau of x is an actual element. So I can split up u into elements of the actual structure. I move them up pointwise and I put it back together. And this gives me the first iterate, the new u predicate of the alpha power, and I keep going. And the iterability means that this process never leads to an ill-founded structure. And you can prove that if you have a non-trivial elementary embedding from L of x into L of x, then you get this structure which is iterable, and the converse is actually easier to prove. So that's an equivalence. Okay, so we have the equivalence of that there be a non-trivial elementary embedding from L of x into L of x to the fact that you have a structure like this, which is actually iterable. If you drop iterability, that's no longer true. Okay. So, okay. And there is much more you could say about X sharp. There is Jensen's covering lemma, which we will not need. There are other equivalences. Jensen's covering lemma actually also leads to something which is equivalent to the existence of zero sharp. And there are other things you could say here, but this is the important point for us. So the existence of X sharp is equivalent to the fact that there is such a structure which is iterable in that sense. And from now on, we will have to work a lot with iterable structures, either structures which look like this or which look very similar. So what we are going to do now is we will move on to structures where there is not even, here you have an external measure. So you have this underlying universe, and externally there is this alpha filter. Now we will move on to structures. You have an underlying universe, but you don't have a predicate for a measure. You only have a predicate for kind of candidates in some sense for a measure. Namely, you will have an ideal. And only when you force, you will get a measure, but then the same thing, we will be able to do the same thing. So forcing will give us a measure, and then once we have a measure, we can take an alpha power. But then by elementarity, in the alpha power, we only just have an ideal again, and then we have to force again to get a measure, and so on. So this is a process I want to describe now, and this will lead to the ℙmax forcing. Okay. So we discussed measurable cardinals, total measures. Now we discussed external measures and sharps, and now we are moving on to discussing ideals and forcing with ideals and getting external measures by forcing with that. Okay. If there is any question, please just ask. So we will now move on discussing ideals on ⍵1 and iterating and generically iterating via such ideals. Okay. And then we will prove an iterability result as we did before for the iterability of V. Okay. Okay, and I want to do that slowly. So let's start out with the first definition. We say that I was talking about filters and alpha filters. I didn't write it down because I was kind of hoping that this concept is familiar enough. Let me write down what an ideal is. It's just a dual thing to a filter. So I less than some kappa. I guess kappa for us will be mostly a regular uncountable cardinal, and in fact we will only be considering the case that kappa is omega 1, but this definition is just general, so this is an ideal. If and only if, okay, the empty set is in, so it's non-empty, that's the same as saying it's non-empty. So if x and y are in the ideal, then the union is in the ideal. This corresponds to the fact that in a filter the intersections are in. So if x is in the ideal and y is a subset of x, then y is also in. And I should have started out by saying that I is a subset. Yeah, I cannot write in this corner. I don't know. That I is a subset of the power set of kappa, right? And usually you would say that the ideal is non-trivial by saying that kappa is not in or something. Okay. Okay, so whenever we have an ideal, we write I plus for the positive sets. These are just the things which are not in the ideal. For instance, by the last line, kappa is not in the ideal, so it's positive. That's a plus here. So this is just the subsets of kappa, so that x is not in the ideal. It's not the complements of elements of the ideal. Okay, so these are the positive sets. What we will do later is forcing with the positive sets, and I will say how that works in a second. Okay, such an ideal is uniform if the positive sets all have size, have maximal size, so there is no positive set which is small. And I'm not sure, yeah, let's see, there is a definition of normality. So an ideal is normal if it's closed under diagonal unions. So I always forget what the symbol is for the diagonal union. So you take a sequence of elements of the ideal and you take the diagonal union. So this is all the psi less than kappa. So that psi is in the, oops. So that psi is in the union of things with smaller index than psi. Okay, so a famous example of that, it follows from the fact that the club filter is closed under diagonal intersections, which is a standard thing which you do in a set theory course, which is the normality of the club filter. It corresponds to the normality of the non-stationary ideal. So a famous example of an ideal is I equals, and this is the ideal we will mostly work with, is the non-stationary ideal on kappa. So this is the collection of all x subset of kappa. Remember that we want to talk about kappas which are regular and uncountable. So x is non-stationary. Non-stationary just means not stationary. Okay, so this is an ideal. If a set is non-stationary, if you have two sets which are non-stationary, the union is non-stationary because each of them is disjoint from a club. The intersection of two clubs is club, and therefore the union is disjoint from the intersection of these two clubs. So you have the first property. If you're disjoint from a club, then your subset, any subset of you is also disjoint from any club. Okay, the empty set is non-stationary and the full set kappa is not non-stationary, it's trivially stationary. So you have all these properties. The positive sets of the non-stationary ideals are the ones which are not non-stationary, which just means they are stationary. So in this context, yeah, the notation is just like this. The non-stationary ideal on kappa plus, right? This object is just the collection of all stationary subsets of kappa. There could be a different notation, but this is what we often use for that. And because the club filter is normal in the other sense, the non-stationary ideal on kappa is normal in the way as we defined it. You can also show that intersections, that the non-stationary ideal on kappa is less than kappa complete, in the sense that if you take less than kappa many elements of the ideal, then the union of them is also in the ideal. Okay, this is true because the intersection of less than kappa many clubs in kappa is again a club. So it's the same argument as that the union of two sets in the ideal is again in. It shows that less than kappa many things are in. Okay. Okay. Okay, I wanted to, maybe we should skip the argument. I wanted to show you the argument why the non-stationary ideal is actually normal, but let's skip that. Should we skip that? There is a lot to do, so let's move on. Okay, so we discussed, so an important example of ns sub kappa is ns sub omega 1. So this is just the collection of all non-stationary subsets of omega 1. And let's stick with this object for now, because this is the only one which will really interest us. Okay, so there is a definition, and all these definitions may be generalized. So in ideal, I is called saturated. Okay, I in ideal on kappa. We say kappa an uncountable regular cardinal. I is saturated if every anti-chain let me first write it down as a slogan, and then I will explain what I mean by that. Every anti-chain in I plus is small. That means if you have a collection xi, I less than theta, they are all positive is an anti-chain. If that's an anti-chain, what does anti-chain mean? It means that if you take, any two elements of that are not compatible from the point of view of I plus, so if you intersect any two of them which are different, then the intersection is not an I plus. So not being an I plus means being an I. So xi intersect xj is an I for all I and j less than theta, I different from j. That's what it means that this thing is an anti-chain. Then theta is actually equal to kappa, or less than or equal to kappa. In other words, for instance, if you have an ideal on omega 1, for an ideal on omega 1 to be saturated, it means that there are no anti-chains of size L2. Okay. We saw an example of an anti-chain before, and even of a maximal anti-chain, namely when we split omega 1 into omega 1 many sets T sub I in the proof that Martin's maximum implies 2 to the L(1) is L(2), then we argued that we could do the splitting in a way that whenever you take another stationary set, then the intersection with one of the ones in the splitting is actually stationary. So that means that there is this, and it's clearly an anti-chain because it was a splitting, so the intersection of any two of them was actually empty, and the empty set is always in I. Okay, so the intersection of any two was empty, but if you take, you cannot enlarge, so it's an anti-chain, but you couldn't enlarge the anti-chain because if you take any other stationary set, the intersection of it with one of these sets is already stationary, so you cannot add it and get an anti-chain. So we had constructed what's called a maximal anti-chain in this ideal. Okay, why don't I write it down, right? The construction of the Ti, I less than omega 1 in the proof of MM implies 2 to the Lf1 is Lf2 produced a maximal anti-chain in NS omega 1 plus, i.e. 1 which cannot extended properly to a bigger anti-chain. Okay. Okay. So there is one feature here. That every maximal anti-chain will be what's called sealed, and this is also an important concept. So suppose let's discuss it for the case that we deal with a non-stationary ideal on omega 1. You could formulate it more differently, but more generally, but let's not do it. So let's say Si I less than omega 1 contained in the positive sets here is a maximal anti-chain. So let's write S vector for this collection. So this is like a sequence like the T sub i's we constructed in this proof of MM implies 2 to the Lf1 is Lf2. Okay, if that's a maximal anti-chain, then S is sealed in the following way. You know, the diagonal union, I think now I'm using it differently, right? So this is the diagonal union. This is the set of all xi less than omega 1. So that xi is in the union of the si's for I less than xi. The union of kappa many things, the plane union of kappa many elements of I cannot be an I. Okay, fine. But I'm sorry, what did I want to do now? What is xi? Sorry, there is no xi here. Can we step back for a second? Okay, so we have this maximal anti-chain, right? So suppose kappa without the diagonal union of the SIs, this were in I. Okay, suppose that would be positive. Okay, because that's a maximal anti-chain, then there is an actual I, so that kappa without that thing intersect SI would also be positive. But then if we simply pick Xi as an element of SI which is sufficiently big, and also Xi being in this set kappa without this thing. Okay, you know, if it's sufficiently big, maybe that's not a good notation now. Let's put a 0 here. There is an I0. So one I0 is fixed and I is a variable. Okay. Okay. If Xi is basically bigger than I, from the fact that Xi is in this thing, we would get that you know, it's the diagonal union. So if Xi is in the complement, it means that it's in particular Xi is not in Si0. So sufficiently big just means Xi is bigger than I0. Okay, that's a contradiction. So if Xi is big enough and it's in kappa without this diagonal union, then Xi cannot be in Si0. And so kappa without this diagonal union cannot be in I plus, because otherwise the intersection would be positive. So from this it follows that kappa without this diagonal union is in I. And when I write I here, I mean the non-stationary ideal on omega 1. Okay, fine. So that means that there is a club C, subset of omega 1, which is disjoint from this diagonal union, right? So rather, sorry, this is in I, so this is non-stationary, so this is witnessed by C. So C intersect this thing is empty. Okay. So that means that okay, so that means that if Xi is in C, then Xi is in this complement. And what does that mean? So there is an I less than Xi. So that Xi is in Si. Okay. Okay, so let's see. So in that sense, the a maximal anti-chain is sealed in that you will get a club, so that every element of the club is also an element of one of the stationary sets which has a smaller index. Okay. Okay, so now I want to move on to showing some nice equivalences, which will become important for us in the future. So we still have like half an hour. Okay, so we now still focus on the non-stationary ideal on omega 1. So there is a theorem. I'm not sure this is really important for us, for what is to follow, but it's kind of nice to know because it gives you a feeling for the non-stationary ideal on omega 1 and what the concept of saturatedness actually means. And also we will have to discuss a weakening of saturation, which is called precipitousness, and it's very elegant to go through the following characterization. And this characterization I'm now about to write down is not that well known, I guess, but it should be. The following are equivalent. The first statement is that the non-stationary ideal on omega 1 is saturated. Set to saturated. And the second is that for all countable substructures X of H theta, so theta here is a sufficiently big regular cardinal. X intersect omega 1 is an ordinal, so we write alpha as X intersect omega 1. If A subset of it's a collection of stationary sets, if that's a maximal anti-chain, which happens to be in X, then alpha is an element of S for some element S of A. Okay, so this second statement is something which is sometimes called self-generic, and we will discuss why it is called self-generic, I guess. So what it means is that you sort of catch your tail. So you look at a countable elementary substructure of H theta, or think of it as a substructure of V. So you look at its omega 1, or in the sense you look at alpha, which is X intersect omega 1. Then whenever you have a maximal anti-chain which is in the substructure, this alpha is actually in an element of the anti-chain. And I forgot to write down that the S itself is also in X, right? So alpha is an element of the anti-chain, which also is an element of the substructure. Okay. So I want to prove this result. So there is a proof. So let's first do this direction. Okay, so we have this anti-chain. We are assuming that the non-stationary ideal is saturated, so the anti-chain has size omega 1, and by the previous slide it is sealed. So okay, so we can write it as, let's confuse it with its own enumeration. Okay. Okay. And we also have that a club which is contained in the diagonal union. Okay, so C contained in the diagonal union of the SI. Okay, because it's sealed in the sense of the previous slide. Okay, and C is club. Notice that if A is an element of the substructure, there is by elementarity such as C, which is also an element of the substructure. Okay, so this is in the substructure, and C is also in the substructure. Okay, but because C is in the substructure, you know, if you take a point below alpha, an ordinal below alpha, beta below alpha, then beta is in the substructure. And then the substructure thinks that there is something bigger than beta, which is also in C, but then this thing which is bigger must be in the substructure and therefore below alpha. So in other words, alpha is a limit point of C, and because it's clubbed, alpha is in C. Okay. But then every point in C is in the diagonal union, right? So that means that alpha is in Ci some I less than alpha. But the enumeration of the SIs is in the substructure. And then if I is less than alpha, the ith point of that enumeration is also in the substructure. So that implies that Si is in the substructure. And this is exactly what we want, right? Now we take S being Si. So S is in the substructure, S is in the anti-chain, and alpha is in S. Okay, that proves that direction. And the other direction, maybe we do very briefly. Let me erase this, then I can leave the statement here. So the other direction is that we are given, now we are given an anti-chain, right? What you want to do is, let me tell you what you're supposed to do, and not really giving the entire argument. So we are given an anti-chain. Okay, so what we want to do is we let xi, I less than or equal to omega 1 be a tower, continuous tower of substructures of h theta, theta big enough, where xi is countable for I less than omega 1. The anti-chain we throw into the first structure. So continuous tower means that xi plus 1 is strictly bigger than xi, and x lambda is just the union of the xi's for I less than lambda. So no problem with that, right? So what we want to do is we simply, we want to enumerate part of the anti-chain A in the following way. So choose some f from omega 1 into A. What I want to do is the following. I first enumerate all the elements of the anti-chain A which happen to be in the 0th substructure. Okay, let's say in order type omega. Then I go to the next model, x1. I already enumerated the elements of A which are in x0, so let's enumerate the next elements of A which are in x1 but not in x0. I can do that in order type omega again. Okay, and that way I can catch up. So I can find such an F so that for some closure points, so that there is a club, such that there is a club C, such that for all I, if S is an element of A, but it's also in the ith model, and here I want to write for an I in C, then S was enumerated at that stage. So S is equal to f of j, some j less than I. Okay, there's no problem with that. I just start out doing what I said, right? So you first enumerate all the elements of A which are in x0, then the ones which are in x1, and so on. You keep going. And at limit stages, you already automatically enumerated everything. And these functions, they catch up. So they were typical, for a typical element, for a typical I, all the elements of A which are in xi are enumerated by f via smaller indices, okay? Okay, and then it's very easy to see that this gives a ceiling of the anti-chain, okay? Okay, so let's not do the rest of the argument. It's very easy to do. Okay. Okay, now we have to move on to something more general. So what I want to do now is I want to define what it means for an ideal, and in particular for the non-stationary ideal on omega 1 to be precipitous. And for that, we need to introduce what it means to take a generic alter power. So in the remaining time of my talk today, which is like we have 20 more minutes, I want to tell you how to take a generic alter power, and then I want to define what it means for an ideal to be precipitous, and this is where we will continue then tomorrow. Okay, and we will do it in a, why did we prove the theorem, which is still on this board? The theorem gives a characterization of the fact that the non-stationary ideal is saturated. We will define for what it means for ns omega 1 to be precipitous, and it will actually turn out that the precipitousness of ns omega 1 can also be phrased in such a way, namely that ns omega 1 is precipitous if and only if, well, it's not true that for every countable substructure you have self-genericity, but there will be a stationary, in fact, a projective stationary set of substructures for which this is true. So this is something I want to prove. It gives a nice characterization. It gives an elegant proof of why saturatedness implies precipitousness. Okay, so let's step back a little bit and introduce generic alter powers, which is really very easy. So let's say AI is a normal and uniform ideal on kappa. Okay, we want to read off a canonical forcing from I. Sometimes people say we force with I. You're not really forcing with I, you're forcing with a positive set. So you order, okay, construe I plus as a poset by stipulating so you say that X is stronger than Y, X and Y both being positive if, you know, X is almost contained. So you want to say that X without Y is in the ideal, right? So you have X and Y. And you want to say that X is almost contained in Y, so this part is supposed to be in the ideal. Okay, so formally I plus together with this relation, this is a poset, and this is a poset we may force with. So so let's say let G be V generic for this poset, then it's fairly easy to see that G gives rise to a V ultrafilter on kappa. Okay, so what I want to say is that we define U to be the set of all X which are subsets of kappa in V, so that there is a Y in G, so that Y is a subset of X. This is a V ultrafilter with nice properties. A V ultrafilter is just, it's like, it isn't V, but it measures all the sets of V. So it is a filter, and whenever if something is in V, whenever you take a subset of kappa which is in V, then either it or the complement is in the filter. So let's prove that. Okay. Let's prove ultra, because I want to do something, right? So let X be a subset of kappa, X in V. So I want to argue that either X is in U or the complement of X is in U. And this is a density argument, okay? I want to show that below any condition, it's forced that X is in U or the complement is in U. So what is a condition? So a condition is just a stationary set Y, okay? And now I have my X, it's just an arbitrary. So Y is a stationary subset of, not stationary, I'm sorry. It's a positive set in the ideal. It's an I plus, and X is just a subset of kappa, okay? Now I look at these two things. I look at this part and I look at this part. One of these two parts has to be an I plus, because if they are both not an I plus, it means they are both an I, and then the union is an I, but the union is Y, and Y is an I plus. So one of them is an I, right? Okay. But if one of them is an I, so either if this part is an I plus, right, then this is a stronger condition, which is a subset of X, okay? So then there is a strengthening of Y, namely X intersect Y, which forces X into U. And if the right part is in I plus, then there is a stronger condition, namely Y without X, which forces that the complement of X is in U. Okay, so that's a density argument. And the same kind of density argument shows. So I don't want to do that now. Let X be a subset of kappa. Y a subset of kappa. They are both in U. Then X intersect Y is also in U. Okay, that's a similar easy density argument. Okay. So that is that will be very important for us. So we are given a normal uniform ideal on kappa. Our kappa will mostly be omega-1. And often the ideal will be the non-stationary ideal on omega-1. So we are given this thing, then we can force with the positive sets, which in the case of the ideal, of the non-stationary ideal will be the stationary sets. And this will give a V ultrafilter. And once we have a V ultrafilter, we can take the alpha power of V by that ultrafilter. Okay. So the situation is that if I is such an ideal, normal uniform ideal on kappa, G I plus, so right, we define this notion of forcing, generic over V, which gives rise to U, all the supersets. So U is a V ultrafilter. So what we can do is we define an elementary embedding. Now this elementary embedding does not exist in V, it only exists once we have this ultrafilter U, which we get by forcing. But then we can do it as before, we can make sense of the alpha power of V by U, or we often write the alpha power of V by G. G and U are kind of the same thing. Okay, you may define this alpha power and you may define the elementary embedding in much the same way as you define the alpha power and the embedding in the case of a measurable cardinal. No difference except for this whole thing exists. So G and J only exist in the generic extension of V by G. Okay. And now there is a key concept, namely the concept of a precipitous ideal. So we say that I is precipitous if this alpha power is always well-founded. We are always interested in well-foundedness. So we say that if for all G, V generic for this forcing, the alpha power of V by G is well-founded. You can formulate this internally. This just means that there is no positive set which forces the alpha power to be non-well-founded, right? I mean, this is by the forcing theorem, this is very easy to reformulate as an internal statement. You don't really have to go to an actual generic extension to do that. So this is what it means for an ideal to be precipitous, and it's related to the saturatedness of the ideal. So this is something I want to finish off for today by stating, and then we will start out tomorrow by proving it, because it's interesting. Okay, so we will say that the following are equivalent. So one item is that the non-stationary ideal on omega 1 is precipitous. And the other one is that the set S of all countable substructures of H. Before we said that in the case of saturatedness, we said that basically every countable substructure is self-generic. So now we have to say the set of all structures which are self-generic are projective stationary. This is what I'm going to write on now. Okay. So let me work with collapses. So X is countable. Okay, I want to say that if M is the transitive collapse of X, and if G is the set of all X in the power set of omega 1 of M, which is the preimage of omega 1 under sigma, intersect M, so that omega 1 of M is an element of sigma of X, that this is sigma to the -1. So for the version of the non-stationary ideal downstairs, this is generic over M, then this set is projective stationary. What does it mean for that set to be projective stationary? This means that whenever you have a stationary subset of omega 1, the set of all x in S, so that x intersect omega 1 is in T, so that's stationary. So it's a little bit more than saying that it's stationary. So S is a stationary subset of h theta to the omega. And now you say that whenever I have a stationary subset of omega 1, and I look at all the x's in S whose intersection with omega 1 is in T, then that's also stationary. So this is what it means to be projective stationary, and then you have this equivalence. And before, so any club is projective stationary. That's trivial. And then by the characterization before, once you have this theorem, we know that if NS is saturated, therefore the set S is a club. So this is just a reformulation if you look at it. So to say what we said before about the self-genericity just means that the set S we wrote down here now is a club. So if NS omega 1 is saturated, then S is a club, and therefore it's projective stationary, and therefore NS omega 1 is precipitous. Okay, so it follows that if NS omega 1 is saturated, then NS omega 1 is precipitous. Okay, so tomorrow we will start out by proving this theorem, which is very easy, but I don't want to start it now. And then once we have the concept of a precipitous ideal, we do the same thing as we did before with external measures. We can just define generic iterations, right? So you have a model with a precipitous ideal, you get a generic alpha power by precipitousness. The alpha power is well founded. By elementarity, you have a precipitous ideal again. So again, you take an alpha power and it's well founded. You take direct limit at limit stages. There is actually a proof, which is a variant of the iterability for V, which again shows that at limit stages, no problem, you don't run into ill-founded structures. So once you have a precipitous ideal, you can iterate in much the same way as we did before, and you never run into an ill-founded structure. So this is generic iterability. So precipitousness implies generic iterability in much the same way as having a measure in V implies iterability of V. And then, for instance, the ℙmax forcing, which gives rise to star, is defined in terms of structures which are generically iterable in that sense. And also these structures will actually be relevant or necessary in order to derive effective counterexamples to the continuum hypothesis. Okay, so let's stop here for today.